Welcome back. So last lecture we discussed about that what is the relationship between the magnitude and the farthest liquefaction manifestation from the epicenter. So, and we discussed in that about the farthest recorded liquefaction feature during Muzaffarabad earthquake of magnitude, or Kashmir earthquake of magnitude 7.6, which occurred in 2015. Now, apart from the liquefaction features, what one can do to understand the ground effect is, and the probability of having the event in near future, and this is purely where we are talking about the geological signatures and geophysical signatures, what we can do. So monitoring seismic activity can also help us in understanding or knowing that this area will experience an earthquake in near future. So there are a lot of studies which have been carried out talking about the seismic investigations. So initially what we do is we try to look at the historical seismicity, because this helps us in understanding that what happened in the past or the recent past, and how the area, in particular the epicentral area, or if you are having the area which is located, as we were looking in the previous section of liquefaction, that it can affect if magnitude above 7 or 7.5, then it can affect the area due to liquefaction up to 240 or 250 kilometers or more. So historical seismicity is important, but yes, the question comes that whether the earthquakes were recorded as we are recording using the modern instruments, but at that time no such instruments were available. So what usually we rely on is the data available in historical chronicles. So if we browse through those informations which are available in historical chronicles, at least we know that what happened in the past. So the detailed study of historical seismicity and close monitoring of modern seismicity as well as geological phenomena. Now this helps us to work out probability of earthquake magnitude and recurrence interval in strategic planning and taking safety measures. Now the probability, of course, there are other two ways also people have been doing, either deterministic hazard analysis or probabilistic hazard analysis, which has been done, which will talk about that what will be the scenario at a particular site of interest in terms of the peak ground acceleration, if you know the source, and what will be the return time of the earthquake in that area. But here what we basically look for is mostly the geological signatures, and the seismologists, they look for the past and present ongoing seismicity. So seismologists believe that the duration of an earthquake is most important factor to mitigate risks which causes maximum damage to the civil structures, failure of soil and slow failure. So these are all related to your geological phenomena. Of course, if you are having the duration, as we have discussed in one of the example from Mexico, that the duration of even the area which was sitting far away from the epicentral zone experienced more duration of ground shaking. This was because of the amplification of the seismic waves in unconsolidated loose sediments. And the secondary effects, mostly what we see is your soil losing its shear strength, as we were talking about the liquefaction, and of course the slow failures. And if the civil structures, the buildings, if they are not constructed considering the proper building codes, of course the poor construction, if it is there, then you will experience maximum damage. Now, example, building can remain standing if the shaking lasts for about 30 seconds, but longer durations, say around 100 seconds, can result into collapse. Even now, people have started taking into consideration the buildings by using base isolations and all that, which can protect your building and absorb all ground shaking. Now, this is an example what during 1995 Kobe earthquake, magnitude was 7.2, duration was 11 seconds, but in same areas located on soft soil, it was amplified up to 100 seconds. And these areas where they were having soft soil mostly were the reclaimed areas, because Japan doesn't have much of the land which is available. So what usually they have done is that they have reclaimed most of the regions around the coastal zones, and that has resulted or caused the amplification. So this amplification of the soft soil resulted into the seismic shaking, which lasted for almost 100 seconds. A magnitude and rupture length can also be taken into consideration, and this information can be used from the recent earthquakes as well as from the paleoseismic investigation. Paleoseismic investigations, we try to look for the paleo ruptures, and that can help us in understanding that how large was the rupture in terms of the length. So if you compare the magnitude, then magnitude in Richter on Richter scale, if you take, and rupture length has been given in this table. So 5.5 can rupture provided it is having an ideal condition to 5 to 10 kilometers, and this is what we say the threshold limit to trigger liquefaction. So around 5.5 magnitude earthquake if you experience, and if the conditions are ideal, saying that you are having near surface saturated sediments, cohesiveness, then you can trigger the liquefaction. Then for 6 magnitude, the rupture length could be around 10 to 15 kilometers, 6.5, 15 to 30, and so on. So now if we are looking for the rupture length for this magnitude, 7.5, 8 and 8.5. Now why I am pointing out this here is because we have experienced this magnitude earthquakes in Himalaya and as well as in Kutch. Of course, in Himalaya mostly we see above 7.5 and which can go up to 8.5 magnitude. Now, if this magnitude earthquake occurs in Himalaya, then it can go up to the rupture length of 60 to 100, 100 to 120, and up to 400 or more kilometers. The area will be ruptured. So this is what we call as the Great Himalayan earthquakes, mainly above 8 or close to 8. So this is the part which is worrisome for all of us. Now, precursory events and short-term predictions have been done in the past, and few successes were been achieved. However, it is a bit difficult to clearly pinpoint when and at which hour the earthquake will occur. It is still we have not achieved, or we have not reached up to that mark to predict the earthquake very precisely. But keeping close watch on the ongoing seismicity based on the instrumental data, to work out the pattern and behavior of small and moderate size earthquake is extremely helpful. Now, before any major event, the velocity of P waves slows down up to 10%. Now, this will happen only if you are keeping a very close watch on the ongoing seismicity, because this will be very important. Now, this P waves velocity will slow down. This is because of fracturing in rock, and later the fractures are occupied by water. So, P wave velocity increases where the water helps to regain the elasticity of the rock. Now, if you remember the seismic wave propagation, and then its velocity is getting affected because of the medium through which it passes, this exactly is what will be experienced. Okay. So, if you fracture the rock, there are open space which will be available, and that will result into the change in the medium, which will result into the slowing down of the P wave. As soon as those fractures or the cracks are filled up by the available fluid, then the P wave will regain its the velocity, and that is because of the change in medium again. Therefore, continuous record of such changes helps in predicting the earthquake. So, this phenomena will happen because what we say is that the crustal deformation is ongoing crustal deformation. So, the rocks within the crust will fracture. The reason of changes that takes place before major events, and this has been given and published in seismological letters. What it says is, due to the plate movement, elastic strain builds along the fault. Cracks begin to develop in the crustal rocks, and the manifestation on the surface may be either the uplift or subsidence before the earthquake. So, land level change will occur in such cases. Now, this land level change, either the uplift or subsidence, can also be complemented by using a dense network of GPS, provided you know where is the fault line. So, this identification of fault line and knowing that the region prone to earthquakes is very much important. So, first, if you know this, then you can deploy more of seismogram, and more of the GPS, close network of GPS can help in identifying the change of the P wave velocity, as well as you can make out the change of land level, that is either uplift or subsidence. This can be well recorded before a major event. So, P wave do not propagate through the cracked rock easily, and their velocity slows down in the area. Radon gas can escape through the newly formed cracks, and the electrical resistivity also decreases. So, these are very crucial or important parameters which one can look for identifying whether you are going to expect a big earthquake in near future or not. Now, the cracks forming phenomena due to increasing stress, because this is because of the ongoing deformation, results into increase in micro seismicity. So, ongoing deformation, cracks are forming, and this cracking phenomena will trigger some earthquakes, but they will be micro earthquakes. So, the activity of the micro earthquakes will increase. Slow downing of your P wave velocity will also take place, and you may also see the uplift or the area is subsiding. Groundwater or semi-solid material from surrounding areas, this is the phenomena after cracking, okay, around the areas flows into the newly formed cracks. As the cracks are filled again by the water, the P wave velocity can increase back to normal. So, this change, and also the radon gas emission decreases, because the radon gas will only escape at the time when the new cracks are formed. So, when the new cracks are formed, radon gas is emitted, but as soon as the cracks are filled by water or the semi-solid material which is available in the surrounding areas within the crust, the P wave velocity increases back, because it regains the fractured area, okay. And at that time it will not allow the radon gas to escape. So, the emission of the radon gas decreases, and this will be followed by a main shock. So, main shock, if is recorded, then the microseismicity whatever was been observed or noticed will be your four shocks. So, these are the four shocks, and even after the main shock we will have the aftershocks. So, you please remember a few things here. One is the P wave velocity, reduction in the velocity of the P wave, and then because of the fracturing of the rocks or the crust, and because of the fracturing the medium changes, and it will not allow the P wave to pass through as it used to propagate through the solid medium. And as soon as this gap, the cracks are filled up by the water or the semi-solid material available in the surrounding, it will regain the velocity. At the same time, you will have more of microseismicity, as well as because of the newly formed cracks, the radon gas will be emitted. But as soon as the cracks are filled up, the emission of the radon gas will decrease, okay, and will be followed by a major earthquake. Apart from that, one can also observe the area getting uplifted or subsided, okay. And this, as I was talking about, this can be done or observed using permanent GPS stations. Now, duration of precursory changes in velocity of seismic wave, the range of such changes can indicate the size of an earthquake. Now, range in the sense the duration, okay, we are talking about. So, for example, the duration could be 1 day, 1 week, depending on the magnitude what it will be. But if you are having the magnitude around 7, then this phenomena can last for almost 6 years, okay. And if you are having the magnitude greater than 7, then sometime the duration of such phenomena can last for more than 14 years or 15 years. So, of course, the time is large here, this time span, but yes, the strain which is required to trigger such large magnitude earthquake is also very large. Like, for example, in Himalaya, along Himalayan frontal thrust, what the paleoseismic studies suggest that the recurrence is almost around 500 to 600 years, okay. So, this is the recurrence interval along HFT in Himalayas. So, once the earthquake has been triggered of say magnitude 7.5 or so, then the next earthquake on the same fault may reoccur after 500 to 600 years. So the time which we are talking here is too short again, but this is a short term predictions which one can do for predicting an occurrence of an earthquake. So it has been noticed that prior to major event, trussel deformation results either in ground shortening or lengthening. So this is what we were talking about, the uplift or subsidence. Also, it has been noticed that always swarm of micro earthquakes are triggered several months before any major event. Bolt in 1993 suggested that continuous upliftment, this is very important, continuous upliftment of coastal area took place for about 60 years. This took place for 60 years near Niigata prior to Niigata earthquake, which was in 1964. The magnitude was 7.5. So the point which we were talking about 14 years, but the deformation was going on since last 60 years in Niigata, and the magnitude was 7.5. So this continuous uplift were been noticed in the coastal areas. And yes, of course, you can notice because there is no fluctuation. For example, I am just putting in sketch here. Suppose you are having a water level over here. This is your MSL. Now, if you are putting the area getting up here, then what you are going to observe is you are uplifting the area. So the new profile which is coming here will be something like this. Okay. So what has happened is that your area has gone up, but the mean sea level has remained as it is, because we know that since last like 1,000 years or more, or maybe 3,000 years, we don't have any major fluctuation of the sea level. So sea level is stable. So the change in the water level here is not because of the change in the mean sea level, but it is because of the uplift. So one can notice, because the landforms will emerge along the coastline. So this observation in such regions, coastal areas, will be extremely beneficial. But the process is so slow that most of the time people ignore it. But the GPS, if you have put, cannot ignore this change. Similar uplift of several centimeters occurred over a period of 5 years before 1983 earthquake in Japan. Magnitude was 7.7. Now, since this region is prone to earthquakes and the deformation is pretty fast as compared to the other regions around the world, people have been very much particular in observing such phenomena. So I'll stop here and then we'll continue in the next lecture. Thank you so much.